today we're looking at integration by parts, which is one of our special BC-only integration techniques. Ignoring this right here, we're just going to get straight into the formula. The formula for integration by parts says if you have the integral of u dv, that's equal to uv minus the integral of v du. If you want more depth about how we got this formula, where it comes from, you can come talk to me. But the idea is it stems from how we get product rule, how we get the equation of two things multiplied together from product rule. All right, so let's look at at an example problem. So this would be our example problem. We have two things multiplied together. We're going to label u as x and dv as cosine x dx. We got to attach the dx to whatever we pick for dv. Now, if we look at the formula, before I write this down, let's go back and look. Look at the formula. For our formula, we needed u, v, and du. Well, to get du from u, we're going to take the derivative of u, which is just going to be 1 dx. To get v, we're going to do the opposite. We're going to take the integral of dv. Now, these should be integrals that you're doing in your head at this point. So the integral of cosine is sine of x dx. So we apply that formula. We say u times v, x sine of x, minus the integral of v du, which is sine of x dx. And then we just integrate sine of x dx. So x sine of x minus the integral of sine of x dx is negative cosine x, so plus cosine x, and then plus c. And that would be our integral. And if you actually took the derivative of this integral, you'd end up with x cosine x there that we had. Now, with this, we need to start looking at how we pick u and dv. I just told you what u and dv is, but how do you actually pick that? Well, we have some selection guidelines. First and foremost, oops, don't want to erase it. Let's get that back. First and foremost, you have to be able to integrate dv. It's a big one. Second, some of your best dv options are e to the x, sine of x, cosine of x, and as a last resort, dx. These things that are easy to integrate and very simple when you do integrate them. Next, I want you to avoid using a product for u. Doesn't mean it can't happen, it just makes it a lot more complex when you use a product for whatever your u is. And lastly, if it gets worse after one step, stop. Now, this is not to say if you have to do multiple integration by parts. I'll show you one in a second where we have to do integration by parts multiple times. That is okay. But if it gets bigger, more complex after one step, then that means you picked something wrong. So your powers should be going away. If you have like x to a power, it shouldn't be getting any bigger. All right, so that's an example problem, but let's look at one where you might have to do it twice. So one like this. You'd pick your u and your dv. You take the derivative and integrate. And this is where, oops, got my dx's. This is where doing these in your head becomes important, because normally e to the 2x, when we integrate it, would be a u substitution. But we want to do that in our head. We don't want to be trying to do a whole separate u substitution just for our dv. So e to the 2x over x, or over 2 is our u, or our v. We'll multiply them together. We have x e to the 2, or x squared, e to the 2x over 2, minus the integral of v du. The 2 and the 2 will cancel, so we just have x e to the 2x dx. And notice, we now have to do integration by parts again. It has gotten simpler. It hasn't gotten more complex. We're losing the power on the x, and we can think in the future, if we keep doing this, the x will eventually go away. But it hasn't gotten bigger, more complex. It's gotten simpler. We just have to do integration by parts again. So u is x, dv is e to the 2x dx, v is e to the 2x over 2, du is dx. So we have x squared e to the 2x over 2 minus. The big thing people do is they forget to distribute this negative. So let's leave that negative there. And we have e to the 2x times x over 2, that's u times v, minus the integral of v times du, which is e to the 2x over 2 dx. Before I move to do that integral, I'm going to distribute this negative, so x squared e to the 2x over 2 minus x e to the 2x over 2 plus the integral of e to the 2x over 2 dx. Now we'll do this integral. That integral is one we can do without much issue because we've been doing it essentially every step before this. We've been doing that integral. Minus x e to the 2x over 2 plus integral of e to the 2x over 2 is going to be e to the 2x over 4 plus c. And lastly, we're going to actually pull out our common factors of e to the 2x and a denominator of 4. So I'm going to say this is e to the 2x over 4 times 2x squared minus 2x plus 1 and then plus c. Okay. There's our final equation. There are some that are a little more complex. I'm going to look at one more that's mainly because it's a special method, but I'm not going to do much more than this. So it's this one right here. Now this is going to happen anytime you see e times either sine or cosine. We're going to have this problem occur. Let's go ahead and do our process. Now, if it's me, I'm looking at e to 3x, and I'm like, I would much rather take the derivative of that than I would integrate it. And so we have cosine x dx, du is 3e to the 3x, v is going to be sine x dx, or sorry, dx is in the wrong spot. Dx should be up here. All right, we'll do our u times v, which is e to the 3x sine x minus v du, 3 integral e to the 3x sine x dx. Now, if you're really forward thinking, you've probably already caught on to the issue here. We're going to have to do it again, but nothing's getting simpler. And so going with the last rule, we said, oh, we should stop and go back. But going and switching what we picked for u and dv isn't going to change this. We're still going to end up with an e to the 3x and some trig function there in the problem. Doesn't matter which one we're integrating or taking the derivative of. So this one's going to require something special. That's what I said. Every time we see an e to the x times a cosine or a sine, we're going to have to do this. So we're going to do one more integration by part, and then we're going to be able to substitute some things in. So we'll say u is e to the 3x again. dv is going to be sine of x this time. du is going to be 3e to the 3x dx. v is going to be negative cosine x. And now we're going to plug it in again. So e to the 3x sine x minus 3, because that minus 3 is on the outside there, parentheses, u times v, so negative e to the 3x cosine x, minus negative, so that's going to be plus 3 integral e to the 3x cosine x dx. Okay, let's distribute this negative 3, and then we'll get to where we can substitute some things in. Now, if you've noticed it, this is the exact same thing we started with. So we're now got what we started with in our problem. So it's just going to be repetitive if we keep doing it over and over. So let's label this. Let's say this is I. So what we've been solving for every step of the way so far is I. Well, that means we can replace this right here with I. So we have I equals e to the 3x sine x plus 3e to the 3x cosine x minus 9i. And at this point, it's just variable isolation. We're going to rearrange to get I by itself. So we have 10i equals e to the 3x. I'm going to pull out the e to the 3x here so I don't have to keep writing it. Sine x plus 3 cosine x. And then we're going to get I by itself by dividing by 10. So divided by 10. And this plus c is going to be our final answer. Okay. All right, so that's the only other tricky one. Once again, remember, this is only when you're doing e to the x times sine or cosine that you have to use this. If you have any other questions, let me know. Otherwise, you'll have a great day.